The lecture 2 begins. In lecture 2, I'll explain differential operator, nabla, and Gauss divergent theorem. When studying the motion of an object in high school physics, the object is a mass point or a rigid body. The position and velocity of such an object are given as a function of time only. That is, time is the only independent variable, and the equation of motion are expressed by ordinary differential equation. However, the motion of the form of continuum, such as a fluid, is given as a function of time and space. As a result, the equation of motion are expressed by partial differential equation. In general, the space is three-dimensional and has three components x, y, and z. If you write partial differential equation separately for each component, the equation becomes long and tedious. If you use the nabla operator, you can write them shortly and concisely. This is why we use the nabla operator. The Gaussian divergence theorem is useful for manipulating and transforming partial differential equations. The nabla operators and the Gauss divergence theorem are not taught in high schools. This lecture series are aimed at not only university grads, but also people with high school level math and physics. That's why the lecture 2 is offered. If you have already understood this subject very well, skip lecture 2 and proceed to other lectures. In addition to the nabla operators and the Gauss theorem, I will explain vector operation and vector product of your for your relearning. Nabla is represented by an inverted triangle. I, J, and K are the unit vectors in X and Y and Z direction. The unit vector is a vector with magnitude of unity or 1. A horizontal arrow is attached above the symbols I, J, and K. The arrows mean that the symbol with an arrow is a vector. A bold symbol is sometimes used for a vector instead of arrow. But in this lecture series, I use the arrow. Nabla is differential operators, but it is treated in the same way as an ordinary vectors. When the nabla operator is applied to a scalar small a, it becomes the derivative of a in the x, y, and z direction. Nabla a is a vector having magnitude and direction. Nabla a is sometimes called gradient a. The nabla operation is applied to vectors too. The nabla operation follows the rule of vector calculation. The rule I will explain from now concerns the product of vectors. You have learned in high school math that there are two types of vector product, that is, the inner product and the outer product. First, let's review the inner product of vector A and vector B. For the inner product, a small dot is put between two vectors. So the inner product is sometimes called A dot B. The inner product of A dot B is defined by the sum of the three products of the same directional component of A and B as shown in the blue line frame. In high school, mass. A dot B is defined as follows, as shown in the figure. The vector B is decomposed into the component that matches the direction of the other vector A. The magnitude of the composed component is B cosine theta, and the inner product A dot B is defined as the product A B cosine theta, as shown in the red line frame. At first glance, the definition in the blue line frame looks different from the definition in the red line frame, but they are exactly the same. The proof is omitted here. Please check it by yourself. The inner product of nabla vector and vector A is defined by the sum of the product of corresponding component. Nabla dot A is sometimes called divergence A. Nabla dot A is scalar. There is a case where a nabla operation is applied to nabla vector, that is the inner product of two nabla vectors. Nabla dot nabla becomes the operation of the second order derivative. Nabla dot nabla is sometimes expressed by triangle symbol. This triangle symbol is called Laplacian operator. Another case is that a vector A is placed before the nabla vector, that is vector A dot nabla. This operator is used to express the inertial term of fluid motion. I explain this matter in the later section or later lecture. Next, I will explain the outer product. The outer product is sometimes called vector product or cross product. To express the outer product, multiplication mark cross is put between two vectors. So the outer product is called A cross B. The outer product A cross B is defined using the determinant as shown on the first line. The 3×3 determinant can be decomposed into the 2×2 determinant. Finally, A cross B can be expressed as shown on the second line. As you see from this equation, the outer product A cross B is the vector. In high school math, A cross B is explained differently. The magnitude A cross B is equal to the magnitude of the area of parallelogram formed by vector A and vector B, and its direction follows the right-hand square rule. I would like to explain the right-hand square rule briefly. Let's make the vector A correspond to the thumb of the right hand and B to the index finger and A cross B to the middle finger. Assume that parallelogram is the head of right-hand screws. When you turn right-hand screw in the direction as shown in the figure, the screw moves in the direction of the middle finger. This is the definition of A cross B taught in high school. This definition also looks different from the definition on the first and second line in the slide. However, both definitions are the same. The proofs are omitted here again. Please check it by yourself. If the same definition of the outer product on the first line is applied to nabla cross vector B, the formula on the third and fourth line are obtained. A cross B is called rotation B or curl B. Next, I will show how description of equations are simplified by using nabla operators. The continuity equation is the basic equation of fluid. If the continuity equation is expressed using the nabla, it is simply nabla.u equals 0. If you show all components of Navier-Stokes equation, many terms are lined up. If we use nabla, you can see that expression becomes very concise. At this stage, you don't mind even if you don't know exactly about the continuity equation or the Navier-Stokes equation. I will explain those equations in lecture 8 and 9 very in detail. Next, I will explain Gauss divergent theorem. There are many theorems and formulas named after Gauss. The Gauss divergent theorem is one of them. When analyzing fluid phenomena mathematically, the expansion and formulation for transformation of equations become very complicated if you don't use this theorem. If you explain the Gauss theorem orally, the Gauss theorem can be said as follows. The volume integral of the gradient A or the divergent A is equal to the surface integral of the scalar A or vector S. If A is a scalar, the Gauss theorem can be expressed by the formula in the yellow frame, where ds is a small surface element and dv is the small volume element. The surface element ds with arrow is a vector and has an altered direction perpendicular to the surface. Its direction is shown by the unit vector n in the figure. ds without arrow is the surface area, which is the magnitude of the vector ds. When A is the scalar, the result integral is a vector because scalar A dot vector ds or scalar A dot vector n is a vector. When A is a vector, the Gauss theorem can be expressed by the formula in the second yellow frame. The result integral is a scalar because the vector A dot vector ds or the vector A dot the vector n is a scalar. The next 4 slides, including the slide, proved the Gauss theorem. I will prove the case where A is a vector. For simplicity, consider it in 2 dimensions. Consider the case and consider the control volume CV colored blue. From now, I will call the control volume as CV. This CV looks like a plane, but it has a thickness of unity. Therefore, the volume of this CV is the area multiplied by the thickness 1. The surface element colored red and looks like a line, but its area is a red line multiplied by the thickness 1. The outward vector n perpendicular to the red surface element indicate the direction of the surface element. The coordinate system is shown below the figure of CV. The vector A has a value inside the CV, but in this sphere, the vector A on the surrounding surface of CV is presented. The small element of the upper left sphere is enlarged and shown in the middle. The coordinate of the center P of the element is x, y. The centers of the west, south, east, and north surface are named P1, P2, P3, and P4. The outward normal vector drawn from these four surfaces are indicated by the red arrow line, and the four surfaces are represented by the symbol delta S1, delta S2, and delta S3, and delta S4. These four symbols from delta S1 to delta S4 are surface vectors shown in the small yellow frame. The magnitude and direction of each surface vector are known from their expression in the yellow frame. P1, P2, P3, P4 are separated from the center by the distance of half delta x or half delta y. The coordinate these points are shown in the bracket. The vector representations of the west, south, east, and north surface are shown together in the last yellow frame. Now let's integrate the vector A along the surface around CV. This integral is the inner product of the vector A and vector ds, delta S. P1 is half delta x away from the center in the negative direction, but y is the same. Therefore, the value AP1 is AP minus round A round x multiplied by the half delta x. Similarly, AP1, AP3, AP4 can be expressed in this way. As in the last slide, delta S1, delta S2, delta S3, delta S4 are given in the yellow frame on this slide. Let's substitute the expression AP1, AP2, AP3, AP4 into the above equation. The expression of delta S1, delta S2, delta S3, delta S4 in the yellow frame are also substituted into the same equation. The result of the above substitution are shown on the next slide. When substituting AP1, AP2, AP3, AP4, and delta S1, delta S2, delta S4, 3, and delta S4 to the equation on the first line, we obtain the equation on the second line and third line. Since some terms on the equation in the equation, the second and third line cancel each other, the number of terms is halved, like the equation on the fourth line. Substituting the expression of vector A with unite vector, the equation on the first line becomes the equation on the fifth line. Number operator is used for the last expression. From the comparison of the first line and fifth line, it is found that the surface integral can be expressed by the volume integral, but this result is relationship obtained for a small element. Therefore, the Gauss theorem has not yet been fully proved, because the Gauss theorem is not a theorem for small element, but holds for large volume. Let's move on to the final stage of the proof in the next slide. Now, let's consider a large volume colored blue. So far, we have expanded the formula for one small element colored thick blue in this figure. Let's consider another small element next to the blue element, such as pink element and green element. These three elements are magnified in the right figures. The surface vector on the east side of the blue element has the same magnitude as the surface vector on the west side of the pink element, but the direction of both surface vectors are opposite. The vector A on the surface delta S3 of the blue element and the vector A on the surface delta S1 of the pink element are identical. So the blue A3 and pink A1 are the same. The integral of the east side of the blue element and the integral on the west side of the pink element cancel each other because they have the same magnitude but in the opposite direction. In the same way, the integral on the surface of the blue element and the integral on the north surface of the green element cancel each other. If you extend the above relationship to the whole volume, it is found that only the integral on the surface of the whole volume remains, and we come to the expression of the Gauss theorem. A small volume element in 3 dimensions is shown in this slide. The only difference for the 2-dimensional case is adding the z direction. In principle, the proof of Gauss theorem in the 3-dimensional case can be done in the same way as the 2-dimensional case. I will finish the lecture 2 at this point. Thank you.